for the nice
presentation. Thank you very much.
And so it's time to move to the last but not least presentation of this session.
Hopefully.
It will be given by Andrea Pferscher from TU Graz in Austria. This is about how to learn the behavior of Bluetooth low energy devices and exploit this thing.
Oh,
Please.
sorry. Okay, thank you for a nice introduction. So in this talk, I will explain how we can use active automata learning to learn behavioral models of Bluetooth low energy devices and how we can use these behavioral models to fingerprint the devices. So in my research, I try to improve the availability of the Internet of Things. However, this is a challenging task since with new communication standards, we will face more and more interconnected devices. One very popular communication standard for short-range communication is Bluetooth. And with the introduction of Bluetooth low energy, Bluetooth becomes also available for IoT devices. So one challenge is that in the Internet of Things, we have to deal with many heterogeneous black box components. We don't know, for example, which Bluetooth low energy chip is used in the device. So the goal of our work is to generate a behavioral model of a Bluetooth low energy device, which is a black box. So we consider this as our system of learning. For this, we introduce an active automata learning framework that basically consists of 3 components. Another Bluetooth low energy device that we use to communicate with our system of learning, a library that we use to compose the Bluetooth low energy packages, and an active automata learning library that uses the Bluetooth low energy requests and responses to generate the behavioral model. So nowadays, many active automata learning algorithms are based on the L-star algorithm from Dana Angren. We already saw in the first talk of the session some work of Dana Angren, and this is another very important work. So she introduced this work already in the late 80s. And this was originally supposed to learn a language with an even number of A's and B. This work was originally proposed to learn a deterministic finite automaton of a regular language. So let's consider this example here, which was from the paper, where we want to learn a regular language that consists of strings with an even number of A's and B's. So for this, we consider the minimal adequate teacher framework, which consists of 2 members, the learner and the teacher. So the teacher has access to the system of the learning, and the learner wants to create a DFA by asking the teacher questions. So the first type of questions are membership queries, where the learner asks whether a word is part of the language, and the teacher answers either with yes or no. Based on these answers, the learner creates an hypothesis, so a deterministic finite automaton, which is then proposed to the teacher. So the teacher checks the equivalence between the system under learning and the proposed DFA. In the case they conform to each other, the teacher responds with yes. Otherwise, a counterexample is provided that shows the non-conformance between the system under learning and the proposed hypothesis. This counterexample is then used by the learner to generate new membership queries and to improve the hypothesis. So we have an iterative approach, which is repeated until we've found a conforming, or the learner found a conforming hypothesis. This approach has been extended for reactive systems. So instead of asking whether a word is part of the language, we provide an input sequence, and the teacher provides us the corresponding output sequence. In practice, you cannot assume a perfect teacher which can answer these equivalence queries. So we replace these equivalence queries by conformance testing. Furthermore, it's not possible to consider the whole input alphabet for many system under learnings. That's why we introduce a more abstract input alphabet, which is then translated by a mapper component to concrete inputs that can be executed on the system under learning. In this case, we learn a model on a more abstract level. So in this work, we consider only the connection procedure of the Bluetooth low energy protocol, which consists of 2 members, or which considers 2 members, central and the peripheral. So an example for the central device would be a smartphone who wants to connect, for example, to a smartwatch. So the peripheral first sends advertisements, and the central scans for these advertisements. If these advertisements are found, the central knows that it can send a connection request, which is then responded by the peripheral. After that, the negotiation phase starts, where the central and the peripheral negotiate upon these parameters. It's important to note that also requests can be sent by the peripheral, and the central has to respond correspondingly. After this negotiation phase, the pairing procedure starts. So our interface for our learning framework, or for the interface between the learning algorithm and our peripheral device, which we want to learn, consists of 4 layers. The top layer is the learning algorithm. So for this, we used an improved version of the STAR algorithm, which learns a mealy machine. Therefore, we recorded our system under learning with our black box device, behaves deterministically, and is resettable. This learning algorithm is implemented in a Python library called LBI, and this allows us to generate this whole framework in Python, which is quite nice. However, we had to do some adaptations to this learning library, so we had to deal with message loss and with non-deterministic behavior. The second layer of our framework is the mapper component, since we cannot learn with considering all possible Bluetooth Low Energy commands. Therefore, we need to introduce some kind of abstraction and assume a more abstract input alphabet. However, it is important to notice that this abstract input alphabet also contains responses, because, as I explained earlier, also the peripheral device can send us requests and we have to respond to them. These abstract inputs are then taken by the mapper component and translated to concrete Bluetooth Low Energy packages. These packages are then taken by the central device. So our last 2 layers are the central device and the peripheral. So the peripheral is the black box device where we want to learn the behavior. So this is our system under learning. The central device is another Bluetooth Low Energy device. For this, we used a device from the company Nordic and flashed it with a custom firmware that allows us to send our handcrafted Bluetooth Low Energy packages to the peripheral. So let's now go to our case study, where we considered 5 different Bluetooth Low Energy devices. For example, one was the Raspberry Pi 4 Model B, which uses a Bluetooth chip from the company Cypress. It's important to notice that all of these 5 devices implement the Bluetooth standard 5.0 and run an example application that sends advertisements and allows us to connect with a central device to these devices. While performing this case study, we faced many practical challenges. So one is that we cannot physically reset the system under learning. This would be impractical for learning these devices because we have to perform a lot of output queries. So we assume that we can reset the device by performing again a scan request. Furthermore, we observed that some of these devices enter some kind of sleeping mode if we execute a long sequence of unexpected inputs. We avoid this by simply establishing a valid connection before and after performing a query. Furthermore, we had to define a response timeout. Therefore, we listen for a minimum number of responses. If we haven't received after this minimum number of responses a convincing answer from the peripheral, we extend this to a maximum number of listening attempts. Furthermore, we have to deal with packet loss. In this case, we always assume that we should receive an answer and a scan request and on a connection request. If this is not the case, we assume a connection error, and this is limited to the maximum number of connection errors. So we can also detect crashes with this. We also have to do non-deterministic behavior, for example, due to packet loss or due to too late responses. In this case, we repeat the query again, but this is also limited by a maximum number of non-deterministic errors. So let's come to our learning results. So our learned models have between 3 and 11 states, and we can learn this model within half an hour and 3 hours. When we look at the last 2 rows of this table, we look at the connection errors in the non-deterministic queries, we see that an error recovery mechanism is required because we observe a lot of connection errors, which are due to packet loss, for example, and also some non-determinism. Furthermore, if we look at the second and the third column, so the second column is a device from Nordic, and the third column is a device from Texas Instruments, both of the model have 5 states, but the runtime of the device in the second column, so the device of Nordic, is 3 times higher than the runtime of the device of Texas Instruments. Therefore, we assume that automata learning not only depends on the state space of the learned model and on the considered inputs, but also on the costs of the connections to the device. For example, waiting for responses. Here we compare the 2 models more in detail. So the first one is from Nordic and the second one is from Texas Instruments. And we see here a behavioral difference on the length response. So we perform an unintended length response. It was not requested by the devices, but we perform it. And we see here that the device of Nordic simply terminates the connection if we send this response. So we have to establish again the connection, whereas the device of Texas Instruments basically stays in the same state and the connection can still be established. The attentive audience might have noticed that represented on the last table only 4 out of 5 learning results or learned devices. So the 5th device was missing. This is now here because we had some problems learning this device because it behaved non-deterministically. The interesting thing was that it always behaved non-deterministically. This input sequence which is shown in the bottom of the slides. So we just tried to remove some of these inputs or one of these inputs, and then we can learn 3 different variations of this device successfully and also generate then deterministic models. But we see, if we look at the last row of this column, that we observe more non-deterministic behavior than at the other devices. The second goal of our work was to fingerprint these Bluetooth Low Energy devices by the usage of these learned models. So this was very easy because after performing a connection request, all devices behave differently. So if we consider the set of all possible outputs and all possible inputs after a connection request, every device has a different set of possible outputs. For this, we can generate following fingerprinting sequence. But there are also other and also shortest fingerprinting sequence. This is just an example. And we see here also the example output for 2 of the 5 devices. So to conclude this work, we successfully learned 4 out of 5 Bluetooth Low Energy devices, considering the whole abstract input alphabet. But we had some problems with the 5th device because this device behaved non-deterministically. However, with just removing one of the abstract inputs, we can learn 3 different variations of this device. Furthermore, we saw that we need some kind of error recovery mechanisms. So we need to deal with packet loss and also with non-deterministic behavior. Furthermore, we successfully generated a fingerprinting sequence, which now allows us to detect or fingerprint these Bluetooth Low Energy chips whenever they are used in an IoT device. And if we want to extend this set of learned models by new BLE devices, we can just learn the models of the new considered devices and then generate a new fingerprinting sequence based also on the already learned behavior. So it's also consistent with the other BLE devices. We don't have to execute tests on them again. So for future work, it would be interesting to consider more Bluetooth Low Energy commands, like, for example, the pairing procedure. Because the pairing procedure also has some very critical security features in there, And that's why we can also then consider or analyze on the behavioral model possible some security issues. Furthermore, we can use these learned models to generate a stateful black box fuzzer. So we can use these models, based on these models, we can generate abstract sequences and then use fuzzing techniques to generate a stateful fuzzer. And since some of these devices behave non-deterministically, it would be interesting not to learn a deterministic model, but also to consider non-deterministic learning algorithms and to learn a non-deterministic model out of these devices. I want to conclude my presentation with a recommendation. So please check out my GitHub repository and learn your own Bluetooth Low Energy devices. So thanks for your attention, and I'm happy to answer any questions.
Thank you, Andrea, for the nice presentation. So as usual, if you have questions from the audience, please write them in the chat or just raise your hand. So from my side, I would have a couple of questions. So the first one was related to the accuracy of the models that you learn. So you use model-based testing in order to approximate a teacher, in fact, which is which cannot exist in the absolute sense. And so is there some risk that the models you learned may miss some useful behaviors from the real system?
Yes, so the focus of this work was really on the fingerprinting part. So we just wanted to learn a model that is sufficient for fingerprinting. So we did not focus that much on the conformance with the real system, as long as we can generate this fingerprinting sequence. But it's true, to do a non-deterministic behavior, we might have the risk that we first learn the very rare behavior. So this is then shown in the model. So I think this method will really benefit from learning non-deterministic models. So that we have a wider range of possible outputs that can happen.
Okay,
but
thank you.
And there are also some other testing methods we can use. So we used for conformance testing simply some kind of random walk, but considering kind of coverage metrics for that would also be very beneficial for this method.
Okay, fine. And a more practical question. So can your system be used for fingerprinting other physical devices than Bluetooth, and with what amount of work from the end user?
Yeah, so this is, so there's, if you interact with other physical devices, if there's a Bluetooth Low Energy devices, you can simply check out my repository, order the device you need to send this custom Bluetooth Low Energy commands, and then you can learn any device you like, or you can fingerprint any device you like. But for other considering other protocols, you have to implement this whole mapper again, and this whole this whole protocol packet composition. But I can highly recommend Cabby for this. So this does most of the work for you. So yeah, so it's basically you can do it.
Okay, thank you. Are there other questions? It starts being quite late for some countries. So if there are no other questions, thank you very much, Andrea, for the presentation and the answer.